In this video, we're going to take a look at scatter plots in Python and consider how they can be used for machine learning. So first of all, why scatter plots? This is an example of a scatter plot that we're about to create from some crop data. And if you take a look, we kind of have an ideal situation here where we see there are certain crops that do well with not a lot of water, and there are certain crops that do well with a lot of water, and this makes sense. If you take something like a cactus and you water it too much, it will die because it's effectively it's susceptible to fungus at that point, and the fungus can kill it, or one of any other number of chemistry reasons why too much water can be a bad thing. On the other hand, you can take a thirsty plant, and if you don't give it enough water, it will die from lack of water. So plants can generally be grouped by their water needs, and a good idea is to plant plants with similar water needs together. In other words, you don't want a cactus next to a very thirsty plant that you're going to need to water frequently. And we see this quite a bit in horticulture and in landscape design, not only with water needs, but also with things like sun and shade tolerance. So a cherry tree needs full sun, but a dogwood or a redbud or even a pawpaw tree wants to be in the shade. So we can group different plants based on these clusters, and that's where these scatter plots can be really helpful for us to visualize things. And these examples I've given you are mostly examples of unsupervised learning. So the example of plants that have similar water needs or plants that have similar sun needs, that could be a case of k-means clustering, where we say, okay, this plant belongs with this cluster of similar plants. Or we could even look at it with k-nearest neighbors, where we put a plant on a scatter plot and we look at the nearest dots near it and say, okay, you must be similar plants. Now, supervised learning is where we're looking at regression, logistic regression or linear regression. And scatter plots are handy here as well. One is we can look at correlation between variables, which is especially handy if we're looking at correlation between a feature and a target, where a target is what we want to predict and the feature is what's going to help us predict that target. If there's strong correlation, then that feature is likely something that's important. However, we also want to look feature by feature. If there's strong correlation between two features, we don't want to use both features in our model because they can interrupt the model, especially if you have a situation where you could predict one feature based on the others. Like, example we hear a lot is the car an automatic transmission? Well, if not, then it's probably manual. So those two are internally correlated, and we wouldn't want to use both in one regression formula. We'd use one or the other. Another place where these scatter plots serve us well is to look at patterns between variables. Here again, if we're doing something like regression, like a supervised learning task, what we might see that there's an exponential pattern from one variable to another. And if that's the case, we have an option to normalize that exponential relationship by applying a logarithmic scale to it, which effectively turns that back into a linear relationship, and then we can model it as part of our supervised learning model. So scatter plots, quite a bit of use for learning. With that, let's jump in and take an example, take a look at an example. I pulled some data off of Kaggle for crop yields, and I want to do a little plotting of those. I've started off the notebook with some imports I know we're going to need, and now I'm going to read in our crop data into a crop data frame. And we see that sure enough we're able to read the data in, but we also see that we have a lot of data we need to throw away. There's several columns that simply are nothing, and several rows that are nothing as well. Let's start by deleting the columns we don't need, and it's typically unnamed colon space and then a number. Note that I simply use the function or the keyword del space and then the name of the column that I want to delete, so unnamed 7, 8, 9, 10, 11, 12, and that gives us a bit of a better data set. Now, I'm not really keen on these column names because they have some special symbols and spaces. It'd be a lot easier to deal with these if they did not have those, so I can rename a column like so with data frame and then rename all one word, all lowercase. Then inside of rename, parentheses, columns equals, and then effectively a dictionary-like structure. So curly and then name colon value, where the name is what we, the current column name is, and the value is what we want to make it look like. We see with this we're able to rename rainfall, make it one word, and also take out the measurement and the special characters. Let me go ahead and do this for the other columns as well. I've kind of created a line here in advance. We see nitrogen gets renamed phosphorus, potassium, and then also yield. Note that in addition to having special characters, yield is actually misspelled here. It should be Y-E-L-D, so I'm going to fix that as well. And we see we have a much easier to navigate set of columns here. Now we do still have several rows that we don't need. So you see right now we have 126 rows, but let me go ahead and drop the ones that are in A. Now we have a concise data set with just 99 rows. Just out of curiosity, let's see what the average yield is, because that looks like a good column that we want to predict. 9.131. Let's make a categorical column for this to say, is this a unit that had higher than average yield or lower than average yield? Because yield is a whole number here, that's going to be pretty easy to deduce. Anything 9 or below will be less than average yield. Anything 10 or above will be greater than average yield. Take a look at how I did this. I used the numpy function where, and then I'm calling out for the column called crop yield, and I'm saying if that value is greater than 9, then give it a 1, which means it's above average yield, and if it is not greater than 9, then give it a 0. And we see that sure enough our yield mean makes sense here. We see the 12 is a 1, the 8 is a 0, 11 is a 1, and so on and so forth. Now let's do some scatter plots across several of these columns that we have. We'll start with rainfall and yield and see how these are related. It's a very easy one line to create a scatter plot. We simply use our data frame and then dot plot and then scatter. And we pass in what we want to use on the x-axis, which here is rainfall, and the y-axis, which here is yield. And we see here this is probably one of the most clear scatter plots we're going to come up with in this demo, because we can see that they're basically two completely different groupings of plants that we have, some that prefer rain and others that don't. Now we could also say, okay, but the ones that don't prefer rain have a lower yield. Well, okay, that could be a function of the type of plants they are. Maybe with plants that don't like as much water, they don't produce as much fruit. But nonetheless, we do see they're able to produce something. Then we kind of have this area in the middle where nothing's produced. So that's a good grouping. Let's take a look at some of the other groupings we can do. If we have nitrogen and yield, we see a bit of a linear correlation here, which is not a big surprise. Nitrogen is kind of like the limiting factor for life because all plants need nitrogen, and it is a mineral that leaches out in the water, where phosphorus and potassium tend to stay stuck to dirt. Nitrogen tends to wash out in the rain. So it tends to be a limiting factor, and basically the more nitrogen we have, the more yield we're going to have. So a bit of noise, a bit of variation in this, but nonetheless, we do see a correlation there that I would expect. Let's take a look at phosphorus and potassium as well. And I realize now phosphorus is misspelled as well, but nonetheless, phosphorus, we see a bit of a correlation there. If this were real data over a large set of data, one thing I would be interested in seeing is too much phosphorus and too much potassium. These are the major macronutrients of plants, but too much fertilizer can be a bad thing. So what we'd likely see is that yield would go up and then yield would start going back down if we were to over-fertilize. Fertilizer is a salt, and so it can desiccate a plant. It can suck the water out of a plant, and that's why you typically don't want to over-fertilize. Let's take a look at potassium. And again, kind of similar with phosphorus, we see a general correlation that the more potassium, the more yield we have, with a bit of noise. Fertilizer yield, we could probably create a couple groupings in each of these where we have high fertilizer, high yield, low fertilizer, low yield. Also see a little bit of correlation, but a bit of noise in that as well. So the one trick with the analysis we've done so far is we're really looking at the impact of one variable on another variable. So rainfall on yield, potassium on yield, phosphorus on yield. Well, the analysis gets a lot more interesting when we can combine some variables. And so I have a little snippet here where we're making a scatter plot, and we're using two different variables here. So in this case, potassium and nitrogen, but then we're coloring the dots based on the yield. Now, remember a while ago, I made a categorical variable called yield mean, where I said, was this greater than 12 yield, or was it, or greater than 9? So it had more than average yield, or was it less than 9, 9 or less? Did it have less than average yield? So what I'm doing here is simply saying, okay, let's create a plot, and let's use a different color to determine if it's high yield or low yield. So C represents color, and C0 gives us a bluish color, where C1 gives us an orangish color. So let's take a look at this. For C and CropDF yield mean, if C equals 1, that means true, then we're going to go with that bluish color. If C is not equal to 1, which means false, then we're going to go with the orange-ish color. And if you recall that categorical column that we had, 1 means high yield, 0 means low yield. So the blues are going to be our higher yields, and the orange is going to be our lower yields. So now we iterate over our plots, and we throw some dots on the map. We throw a couple labels on, and we see that this is what we come up with. So we can see potassium and nitrogen. We can see that those plants that have low, both potassium and nitrogen, tend to be lower yielders, where those that have high of both tend to be higher yielders, with a couple exceptions. And those exceptions, we could dig in and see if they're outliers. We can change this to phosphorus. And again, take a look at a similar correlation where lower nutrients tend to give lower yields, higher nutrients, higher yields. And we could try that with any combination of our two variables. Of course, we can do this manually, but we can also come up with something called a scatter matrix, which we'll look at in a future video, where we just automatically throw up several different combinations of variables and look at their relations. But the handy thing about this is this opportunity to use color to add yet another dimension to our visualization. This has been a look at how to use scatter plots with a data set where we chose 5 different columns to figure out how we could possibly group these for unsupervised learning, or how we could group them even for supervised learning and make models out of different groups, or take a look at the relation between different variables and different groups. So this is a fairly straightforward plot. Stay tuned. I have another video where we're going to look at a scatter plot matrix, where we can look at the relation of variables one by one in a matrix. So have a look at that. Much more to come. Thank you.